Welcome everyone to the Immutable and Reproducible Software track at scale 21x. Our next talk is going to be by Raina and Shaun talking about FBInstance to MetaInstance. And with that, I'll let you guys take it away. Thank you.
Thank you everybody for coming here at 6:15. There is America Talent right next door, in case you got lost on the way. Today we'll be talking about our journey from running our compute workloads on long-running instances, the lessons we learned, and how we transitioned that to an immutable architecture as a result of those lessons. My name is Nish. I'm a production engineer at Meta. He's Shaun. He's also a production engineer at Meta. My title internally is far worse. So we are part of the Cloud Foundation team at Meta. It's one of the many foundation teams in the company whose job is to oversee all the building blocks covering a specific area to ensure it's intuitive, reliable, and secure. In this case, it concerns cloud. Our job is to make tooling for other teams within the company which run the application themselves. This means that we fix the problems with interfacing with Meta on-prem. We call it prod, and cloud. This is a pretty giant problem space in of itself because Meta is a very mature on-prem shop, which means that there are a lot of existing solutions, and there are a lot of abstractions and lots of integrations to be done. By the way, that's my title inside the company. I told you, it's worse. So let's start by asking the most basic question. Why are we here? And why should you listen to us? Meta is a big company. We are in this unique space where we invested heavily in building our own data centers and even our own hardware at some times. We might have seen some hardware in the booths if you stopped by in the last 2 days. We still do have a lot of usage of cloud as well because there are some use cases we run where data center does not meet our needs. And as a result of it, we invested heavily in cloud as well, and we have a mature ecosystem there as well. We are hoping that this talk will provide some insight to people who are in a similar position as us and are heading towards it. We think that the conceptual problems we are solving are not unique to us, and anybody else who will be trying to straddle two worlds of cloud and their on-prem infrastructure will have to face the same challenges and problems. And one of the biggest problems is the topic of this talk. And it doesn't matter whether the company is big or small. These problems are not unique. So the story begins with FBInstance. It's an EC2 instance. We call it FBInstance. Yeah, that's when back we were called Facebook. You might have heard of it. You might have downloaded the app on your phone once in a while. Might be even using it. So what does an FBInstance mean? Before we talk about that, let's take a snapshot of history when cloud was still starting out in the company. Our on-prem was already a well-oiled machine, pretty mature, and we had gazillions of hosts deployed across many countries and continents and data centers. Please don't ask me numbers, I don't have them. The Facebook hosts were very specific, had very specific features, and very silent features. They are very homogeneous. They are CentOS based, all of them. We pretty much run CentOS across the board. Back in the day, it was CentOS 8. We do configuration management with Chef. So basically, all the hosts are deployed once, and they are long-running hosts. And once the hosts are brought up, bootstrapped to the data center, we then go on using Chef for configuration management. And since from that point onward, Chef is the one which drives all the upgrades and everything. We are very strict about this, meaning that we never really deviate from running any other flavor of CentOS even. We don't even run Ubuntu, we don't run anything else. And it has been working very well for us because it allows us to expand very rapidly to newer regions, build new features, remediate problems, and in general, the fact that people have familiarity with the tooling really helps people learn quickly and us to bootstrap or new developers on it. So when we were thinking about how our strategy for our hosts in cloud should be, two of the main things stood out. One was that we wanted to build a compute platform which looked like our internal hosts. So that the same tooling which people are already familiar with in the company will translate very well into the cloud ecosystem. This also meant that a lot of the tooling was going to be translated, and a lot of the problems which were solved, as like logging and metrics, which we have internal solutions to, were we reused. And we don't have to teach all those things to the users again, and they will be able to integrate that quickly, and all the company products which work downstream from that will just work seamlessly. The other problem we had to deal with was that cloud was a completely different environment, and our on-prem environment is very locked down, meaning that it requires a high degree of bar to even access in the first place. So we had to build this infrastructure and a set of security guidelines in really high bar to even access any service running inside the company. So those are the two things we started with. Now, on the next slide, let's see what the actual host looked like. On the left, you will see a classic layer-by-layer diagram of FBInstance host. And as you can see, it was running in cloud. And on the right side of the line, or vertical line, you'll see the on-prem stuff. And there was a very simple connectivity between the two. It looks simpler here, but in reality, that line is much more complicated than that. It requires a lot of hops to get through and a lot of validations in place to be able to even make it through to the on-prem ecosystem. The host itself was a multi-layered architecture. We started off with the internal CentOS build. We do maintain the upstream. We do maintain the upstream, and we kind of keep updated with that. But we deploy a lot of internal packages and internal patches of things for more tailored to our own internal needs. So we are taking that build as a starting point, and then we used to build AMIs within that. And this is what ran as a result. And that host layer bootstrapped. We had a bootstrapping layer on top of it. And that's where we did all that familiar tooling. We brought it up. We basically run the Chef bootstrapping there. And then we added access to data registries, which were our internal versions of packages and our internal repos. We did not talk to the open source repos. We had our internal repos we had access. And all of that required broad connectivity. So we also had a certificate management inside, so it required the authentication to be done so that we could talk to our on-prem infrastructure. Sorry. That kind of was the layer which ran once when the system was bootstrapped. And once the system was bootstrapped, by the way, in the same time, in the same bootstrapping layer, if a user had to do something, they could also introduce their own applications and then put them in that same place in the user data of any instance to bootstrap it once. All of this layer was implemented in the bootstrapping user data of AWS. You might be familiar with that. But there were other places where we will do that same thing as well. But it was basically done at inside the post-booting, post where the OS booting. Once the bootstrap was done, the Chef layer took over. And then Chef was the one taking care of all the updates and patches of the system. And that's something we ran every 15, 20 minutes or so. So it was always patching things and always downloading new code. And that's the one which is responsible for creating all the logging and all the metrics connectivity and maintaining the existing DNF repos and making sure that any new upgrades were patched in, and also making sure that the product connectivity was maintained. And all the security certificates were up to date. If the user wanted to do the same thing with their own applications, they could also set up their own bundles or could derive from our bundles on the side and could run them next to the same runtime layer. If you look at the dot around that, that kind of means that they were constantly changing. Lastly, even if the users were not running their things in Chef, they could run their own workloads as their own applications outside Chef if they wanted to, and some of them are running them, but they had no control over their lifetime, and they were outside the system. This was kind of a less, not as common of a scenario. And one thing to note from this diagram is that at the bootstrapping layer and at the runtime layer, we were replicating the same work. We were trying to control the DNF registries, and we're trying to control the user agents. We're trying to control the product connectivity. The on-prem connectivity. And then that will hint to problems coming ahead. there were a lot of problems with this method. One of the main ones was operation burdens with Chef. There were problems with dependency management. There were problems with the infrastructure as code coupling we had, and we'll talk about that in more detail. And there was also a problem with the actual network connectivity to the on-prem infrastructure. I'm telling this to myself. This makes me feel less stressed. The Chef is usually a fixed forward sort of system, which means that if there is something wrong with the Chef code and it breaks on a running instance, the only way to really fix that is patching the code and fixing forward. There isn't really any culture of rollback, and the tools are not really assuming that. That's something which was kind of problematic for us, because every time you had to get rid of a problem in Chef is by updating the code, making sure the bundle builds and then pulls a new code and then redeploys it. The other problem was that, so one of the things here is that if one cookbook in Chef breaks, it will basically break the whole deployment and it'll hold up the whole deployment. If you had a run list where the second recipe broke, all the other recipes beyond that will not run. And you'll have to fix the second recipe before you can even run it in the first place. So until you haven't fixed it, you are basically not patching anything. The other problem was that, as I mentioned before, our on-prem infrastructure was very homogeneous, meaning that all the CentOS 8 distros we were running were exactly the same. But in cloud, that inherently was not true because users could change the host at Bootstrap to whatever they wanted, which included changing packages or configuring something differently. And it also meant that we never had a homogeneous layer to work with. And that meant that if we had tested a layer with a certain version, that did not mean that it'll work for all the possible deployments out there. And that indeed will be the case where we will have real cases where people are using the same AMIs as us, but they will still break because they were trying to do something custom in their bootstrapping. As a result, we were always playing catch up with our internal Chef cookbooks. Many cookbooks actually came with on-prem assumptions because they were written for on-prem stuff in mind. And then they were constantly and rapidly getting changed. And the velocity of that is really crazy because there were a lot of people who are changing the code all the time. And if any dependency was not tested on our own host, and that was not always the case, that they will test because of the challenges I mentioned before, it will always keep breaking us. And we will always have incidents trying to retroactively fix it. The other big problem we had was as we deployed this and learned from our customers, a lot of the customers were in the cloud for reasons which did not require any CentOS. They wanted to run other OSs. They wanted to run Amazon Linux. They wanted to run EKS. They wanted to run Ubuntu. And the fact that we were locked into this environment basically disabled us from trying to expand them and give them any platform or tooling in those platforms, in those OSs. So that kind of was already binding us. The other big problem was dependency management. As I mentioned before, we had internal CentOS build. So that when we did the internal CentOS build, we were adding some customizations and packaging, and that included adding DNF repos and DNF packages. And then we were taking that image and building the AMIs. The AMIs themselves, at that point itself, we will install more packages and things like that. And then when the bootstrap happened, there was another time when you could go and change the DNF repos and install some other packages. And eventually, Chef was responsible for installing further packages. So there were 4 layers of dependencies where the RPM could change. And in order for things to work, all those 4 layers had to be kind of in congruence with each other. And if any software was installed which was not compatible with the layer above it, it will break it. And that indeed happened a lot. We will have a new version of some new software coming out, and that was required downloading a bunch of other things. And we hadn't really tested it, and that will show up in Chef runtime and will break other packages dependent on it. A very common example of that is systemd, because systemd is not just one package, but a collection of many packages. So if one package upgraded, the other packages at the same time were not upgrading, and then the dependency was completely messed up. And this happened quite a lot. Another problem we had because of this layering is that we didn't have any, like usually when you have this kind of problem, the easiest thing you will want is just roll back to the previous version configuration, right? But we didn't have one because these 4 layers were creating so many different permutations that we couldn't actually pinpoint a working configuration and go back to it. In fact, in some of the cases, the chef cookbooks were not retained for a long time anyways. So there was no good configuration to roll back to. And because of that, we always had to fix things forward. Another problem which constantly keep running into was the 15-minute upgrade problem versus the 6-month upgrade problem. On-prem, we deploy hosts once, and we continue to update and patch it over the full lifetime. This is not the case in cloud, where it's very cheap to just discard the host and start over. And what happened in those situations was that, imagine you are running a host today, and you built that with Chef and you tested it, and then 6 months later, you threw the host away and started off with a new Chef. It didn't mean that that Chef version will be compatible with that day's AMI version. And it also didn't work the other way around. If you deploy the same AMI version today, and you roll back to older version 6 months later, it didn't mean that the Chef version will work with it. So we always had these kind of problems, where the layering just didn't work. This is a very peculiar problem. We had infrastructure as code of choice. Terraform was our infra as code of choice, and we were using that as a way to configure these hosts because we had a lot of customizations going through the user data into these hosts, and that's kind of what I'm kind of highlighting here. The DNF repo configurations, the Chef bootstrapping, and the user customization, they all went to user data. What this meant was that this configuration was locked in during the Terraform apply time. If user didn't apply Terraform, if we had any updates to be made here, they won't actually translate to their actual deployment. We tried to make this easier for ourselves by making modules and encompassing all the customizations in the Terraform module. But even then, a specific user will have so many accounts, and they have to apply the same configuration on every account in order for us to even be able to make any changes and be able to get the newer features. While all this was happening, Chef was constantly running every 15 minutes. So we didn't really have a way to consolidate or like reconcile all the different versions of things we were running. We basically were running completely different versions of OSs at any given moment. So that really limited us to fix the problem in the first place. All the things we were talking about here, we couldn't really fix them because that would have meant making an incompatible change on Chef, which might break the host, and then the Chef run will break. So we had to be really careful with what exactly we could roll out. So that kind of tied us as well. Right? It was a pretty major factor. All these problems I talked about, all the last three slides, meant that if on a good day they worked, and that was kind of the barrier of entry to even get the on-prem connectivity. If all the three things before that did not work properly and flawlessly, we won't even be able to get to any services in our on-prem infrastructure. And a lot of the times, that was one of the main reasons why anybody was even using it, because they wanted to, those use cases were very common, that somebody was running something in the cloud and they wanted to talk to on-prem. In order to get to on-prem, one of the main things was actually downloading the bundles themselves. So we were in a situation where a cookbook will break us, and then we won't be able to upgrade it because we had to get on-prem connectivity. And if the cookbook was breaking long enough, we'll lose the on-prem connectivity, and we won't be able to get out of this cycle. It almost looked like a catch-22 situation, which looked like a snake rearing its head and eating its own tail.
Can you hear me? Okay, cool. So in reality, it looked more like this. So we started asking ourselves, like, where are we going to go from here? Because this isn't sustainable. We don't like this. We're getting woken up in the middle of the night. Like, what can we do about it? And we kind of knew where we wanted to be, and that was something with immutability. So to us, immutability, I feel like that the definition is not the strict one. Like, to us, it just means we want all the bootstrapping dependencies to be baked into the host. And we know that away and start a new one, which kind of implies we're not going to be using Chef to update it. So instead, we had to rely on all the CI/CD tooling we built to throw away these hosts and bring them back, which also kind of implies we had to be okay with a shorter life cycle for those hosts. In addition to immutability, we knew we were going to want to support multiple distros. So as Nish mentioned earlier, there was only support for CentOS 8 at the time. We started getting pushed to support this, this new fancy thing called HPC and Kubernetes as well. So those, the AMIs that are best used for those applications in AWS are Ubuntu for HPC, and then unfortunately for us, Amazon Linux for Kubernetes. And we knew we wanted to support both of these, so it kind of led into us having to figure out, okay, well, if we're going to support these distros, how are we going to bootstrap them? Like, we can answer it for CentOS, but we want a consistent way to bootstrap all of these distros. And if we were going to bootstrap them, we want a common way to download basically all the binaries that our platform supported in a consistent way to run them, install them, fetch them, and things like that. So we started asking ourselves, okay, like, now we know what we want, but like, how can we get there? And we sort of settled on this. Systemd and Containerd were really all we needed to get there. We'll go into why. So Systemd kind of gives us that consistent bootstrapping story we're going to need if we want to make the same guarantees that as we support different distros, they're going to come up and behave the same way. And OCI containers or Docker containers, more specifically Containerd, allows us to package up our platform in individual units that are actually portable across these distros, and really just allows us to focus on figuring out, like, what is it that we have to do so that when we run that container, it thinks it has access to the full host, but it really doesn't. This sort of allowed us to focus instead of targeting every distro we wanted to support and then maintaining a version of our platform for each of those distros and then handling all the like combinatorial explosion that comes with that when, like, you know, binary 1 wants this version of that library, but on a different distro it's something else. We just said, like, all platform binaries are going to run on CentOS 9, and we're just going to put them in containers, and then for each distro we'll figure out what bind mounts we need to set up so that the platform thinks it has access to the full host. Which then led us to sort of ask ourselves, like, would it be possible for us to even pull this off? As we mentioned earlier, Chef was sort of the blessed way to do pretty much any computing or host management at the company. And we just tried anyways. So half the team was already invested in building these pipelines and this tooling for supporting Kubernetes, which kind of meant we were getting familiar with building containers frequently and really just getting used to this idea of building a whole OS and then just throwing it away anytime we wanted to make a change. So we were like already halfway there. Like, we already knew we were going to support Kubernetes. We were already trying to put our platform into containers. We sort of realized, like, what if we could just use this to solve the host problem as well? So we realized we could, and we called it MetaInstance. That happened after the company rebranded, so it just felt like the right thing to call it. We knew it wasn't going to be called FBInstance 2 because it didn't really make sense. So we went with MetaInstance, and like the first thing we committed to was, okay, this thing is not going to run Chef at all, and then we kind of conceded and said, okay, we'll leave Chef there, but we're not going to actually use it to drive the state of the system for pretty much anything unless it's patching like a CVE or something like that. With the understanding that even if we did that, we also need to go rebuild the OS so that we can remove the Chef change as soon as possible. As far as bootstrapping goes, we lean heavily into Systemd. And as mentioned earlier, we put basically the entire platform into their own individual containers. Oops. So I want to show you what that looks like, but just real quick, I want to show the FBInstance, and then I'm going to flick back and forth, but it should kind of look good, so bear with me. Just to note, like, we have the OS layer on the bottom, and then we have these various layers here that Chef is handling, and then at the very top, the user workload is there. This is what a MetaInstance looks like. So notice we still have the OS layer, but now we're supporting multiple distros. And we have this new thing here, which is the containerized MetaInstance layer. And each binary we want to support in our platform has its own container. And like, if we can bring this MetaInstance layer to any distro, then we basically support that distro, and our users can kind of rely on that. We hope they don't, but we get all the benefits, right? So in the case of Ubuntu and deep learning, we get to run the kernel with the right patches and the right CUDA versions and things like that. And in the EKS case, we're running Amazon Linux, which is, we'll get into why that could be good or bad, but it comes with the kubelet pre-installed and things like that, so it's the thing we should be using. At the top, we have the user containerized workload layer, which is where we want our users running their workloads. And we, at the same time, sort of push them to put their workloads into Docker containers, because getting a MetaInstance basically means getting a host that's pre-configured to talk to prod and do the nice things like automatically give you metrics and logs and various telemetry. But it also means you have access to containerd, so you can just run your application. You don't really have to think about authenticating with registries and things like that. So what did it give us? The first thing it gave us, probably the most important thing, was portability. So one of the goals was we want to support these multiple distros. We could now do that. All we really have to do is implement that yellow MetaInstance layer, and we're now supporting that distro. Additionally, we could pick up our platform and put it in Kubernetes. So speaking of Kubernetes, this is the bare MetaInstance, but it wasn't much of a stretch to support Kubernetes. The only difference here is we're swapping the base distro for the Amazon Linux EKS image. Notice we still have the MetaInstance layer here, but now we sort of unlock this ability at the top to reuse some of these same components in the green there. So when our users are running their applications in pods and they want their logs back in on-prem, it's the same daemon that we're running on the host. It's just sort of enlightened to sort of figure out what the Kubernetes workloads are doing and put them in the right places. In addition to portability, we got predictability. So now that the hosts were immutable, it meant that we could test them. And if they failed in the CI pipeline, it probably meant they were going to fail when we went to deploy them. So we just didn't deploy them. If we stopped the CI pipeline, we would figure out why, and we would fix it, and like, that was it. Rolling back actually became possible, because instead of trying to figure out the like 6-month versus 15-minute versus build time sort of problem, we just started the old version that we knew was good and worked on fixing the current one that was broken. And lastly, it just sort of gave us and our team, which is roughly 5 people, like simplicity. So instead of splitting the team in half, where one could sort of focus on building container images and how we were going to do Kubernetes, and the other half sort of diving into all the fires that came with running Chef, we could sort of consolidate our efforts around like, okay, we're already going to invest in this container tooling anyways. We might as well just have everyone learn how that works, sort of cut off the Chef part and use as much as we can of it to solve just the generic host problem in addition to the Kubernetes problem. And we were also able to cut out a lot of the complexity that Nish had mentioned earlier in our Terraform module, which had all the weird like bootstrapping logic that the users couldn't really customize and we couldn't really customize and things like that. Instead, since we now baked all of the bootstrapping logic into the image itself, we just start the image, and it's a lot more reasonable to work with. But it wasn't like all perfect. So our new pane is sort of dealing with the small systemd splay across the distros we want to support, especially in Amazon Linux. It's running a really old version of systemd, so we're constantly making decisions about what features we want to use and if we want to diverge per distro and things like that. Same with Cloud Init. But so far, it's a trade-off that we're happy to make if it means that all of our failures sort of happen at CI time. And we introduced a lot of new learning curves for ourselves and especially our users. So Docker sort of became this you must be this tall to ride kind of situation for a lot of our users. And at Meta, we don't really use Docker internally. So it was a little bit unfair to sort of expect Meta engineers who come to us with a compelling use case and need to use the cloud to suddenly have to learn how Docker containers work to even get their VM going and things like that. Additionally, like as much as we had pain with Chef, it was expressive. It was easy to sort of write things in a very short amount of code and sort of get your point across. Now everything is Bash, so I hope you like writing Bash. And like the last thing was, I think most people really like to get their host and just like leave it running for as long as possible and not think about what happens when it reboots. Well, now that the image is immutable, we expect hosts to reboot frequently, so we have to get people on board with using CI/CD and like constantly recycle their hosts and things like that. So as takeaway, moving the host configuration to build time like significantly improved our quality of life. We're no longer waking up at 2 a.m. because someone somewhere in the world released a new RPM that's incompatible with the rest of our stack and things like that. Almost all the failures happen in CI now, so that means like no big deal. The CI pipeline turns red, but there's nothing that you have to jump and like get on top of. You can get to it when you get to it. And if you're going to support Kubernetes anyways, you might as well just reuse those same containers. Really all you have to do is figure out what configuration change is needed to run the same thing on a host where there's no Helm, where there's no kubelet, and things like that. And when you containerize your platform, it becomes like very obvious in the future when people need to extend it. So we have teams internally coming to us saying like, hey, we want to run our daemon on all of the hosts. Like, what do we do? And the answer is pretty obvious for us. It's like, go look at how we set up our entire platform and just copy one of the images and make it your image and run the same install script. And you're basically, you're part of the MetaInstance platform now. So that's all I have. If there's any questions, let us know.
I think we have about 25 minutes for questions, so let's get started. I'll be running the mic back and forth if Shaun needs to answer.
I have two questions. First one is, you guys are using systemd as a bootstrapping tool. Is that using systemd make OSI tooling or something else?
Just vanilla systemd.
Yeah.
Just, yeah.
And then second question, what measures are in place to ensure the deployed image remains immutable over the lifetime of the instance? Something like dmverity, I guess, would ensure read-only properties.
So the way we do that is, what do you mean by ensure though? The question is, what?
To ensure that the lowest layers in the stack remain read-only.
This is an easy answer. We don't. So it's just like I think this is sort of why in the beginning I tried to prefix it with, this is what immutability looks like for us. It's not the like true, like everything's mounted read-only and it's impossible to change or anything like that. We're happy enough with where it is now, but we definitely like recognize that that's sort of the next hop.
I mean, to add to that, I think the other thing is that if something breaks, we will know about it. So in a way that if somebody changes something under the cover and it isn't immutable, we will catch it. So there is not really any way to, like I was trying to understand like with the question, but like there's not really a way to like make it unimmutable because everything is already done at build time. The runtime capabilities are not, we don't actually deploy Chef. So.
I'll stick with the systemd as a theme. So I think with Meta's made so many contributions to systemd, I assume pretty modern, running on premises. How do you manage all those different, use it like lowest common denominator type situation, or just how do you manage multiple versions of systemd?
So the question is, how do we manage all the multiple different versions of systemd considering we are pretty major contributors ourselves? So the answer that's easy. We don't have to worry about what version we run internally because we are freely able to use the systemd version which ships with the image. So in the Ubuntu, whatever version we're using, whatever systemd works with it, we just use it. And what is dictating that is basically the most oldest version of systemd, which ends up being the Amazon EKS AMI. And that's what we do.
Yeah, just to point out, like we're not locked into using Facebook or Meta systemd, but we were when we were running Chef because that would just install it and we didn't really.
I think one thing probably what I pointed out earlier was that the CentOS version we're running now is not the internal CentOS anymore. We're running the upstream version. So we are just running CentOS 9 stream vanilla. And we're not running any internal DNF repos either. We just run upstream.
So for your containerized meta instance layer, you know how you containerize Bootstrap, logging, metrics, prod connectivity. So I guess you have a brand new host. It ships with Docker and it ships with those containers.
Yes.
And does Kubernetes manage those containers, or just like a Docker file, Docker compose?
So actually, I'll go back one. So in this case, where there's no Kubernetes at all, these are all installed at build time. And systemd will bring them up when the host boots, but there's no Kubernetes at all here. And then one decision we made, like we started off thinking like, hey, why would we run the same daemon twice? Like we're already running Kubernetes, like why don't we just let Kubernetes manage the setting up the logging, the metrics, prod connectivity, and things like that. But what we decided was to go the other way, which is even if it's a Kubernetes node, it's still a meta instance. So at this layer, these are all baked into the image at build time. Systemd is turning them on. But in the green layer, like once it becomes a Kubernetes cluster, those are installed via Helm charts and things like that.
So there are actually situations where that's why there are two CI/CD pipelines over there. The host CI/CD pipeline will swap the host, and while that will have its own schedule, and then the Helm CI/CD will swap the pods. So both are running the same time sometimes.
Hi. I want to let everyone else have a question. I actually had a question for you guys. You mentioned in the migration from Chef to more the tooling you had with your CI/CD that you had to embrace shorter life cycles for your instances. Can you explain more about that and like why that was?
So like embracing it wasn't as much of a thing we had to do as much as it was something our customers had to do. And it wasn't so much that they wanted to be a part of that process, but really it just came down to like a compliance thing. Like what is our acceptable window by which we will allow like what could be a host with an issue to run without being patched. And we kind of just agreed with some security folks on like a specific window, and we made sure that we had tooling in place so that our customers could meet that obligation in as easy a way as possible.
And just to note that this is basically impossible in on-prem systems because you can't really throw away hosts. So they have to rely on Chef to meet that obligation. So a good example is that if there is like a CVE coming out, and you have to, it's very easy for us to deploy that on-prem to just like fetch everything quickly and then get rid of it. It takes like a week tops, but story is different in cloud.
So you mentioned you still have Chef there, in case of CVEs and things like that. So since moving to MetaInstance, how often are you changing the runtime, say, with Chef or like some other system?
I think never. I don't think we ever had to do that so far. Maybe once to send some metadata and stuff, because we still want to capture the metrics and things like that, but that's mostly metadata. Nothing actually runs on it.
Well, if there's no other question, oh, wait, one more.
So instead of dealing with Chef convergence issues, I guess you're just punting this all to CI/CD and letting Docker, systemd, and Kubernetes sort it.
Yes, pretty
Got
much.
it.
Pretty much.
I'm going through the same issues, so I was like, oh, that's pretty.
That's why I mentioned in the beginning that it's not unique to us.
Is the change primarily because of moving away from on-prem to the cloud, or is it more for making sure the applications run in the Kubernetes environments or containerized environments, or a mix of both?
I think it's a lot of different reasons because the use cases are very unique by themselves. And by default, the reason they come to us is because whatever they want to do doesn't work on-prem. So they are by definition kind of out of the middle of nowhere. So they're all over the place. There's no homogeneity there. There's no pattern.
Got it. Thank you.
Okay. Oh, one more. All right. Keep them coming. We still have time.
I guess since you mentioned HPC, right, as like one of the applications you want to support, how do you deal with apps that have not only a specific software like distro requirement, but also have a hardware requirement, like maybe they need a certain network interface or GPU?
That's a good question for sure.
Yeah. Okay. So for HPC, you can kind of imagine these purple boxes are like Slurm. So we basically containerize as much as Slurm as we can, and there's like CUDA down here. There's special NVIDIA drivers and patches and things for AWS where where these hosts are running, and it's really a game of figure out everything you need to bind mount from the host and like match it up with what's going on in the container. So it's not just like this clear-cut thing that, oh, since we want to support HPC and we have this layer, like everything works great. We still do have a lot to work through when it comes to containerizing Slurm and all of its components and things like that. But it is running containerized. It just really comes down to like figuring out what the bind mounts are and supporting the correct versions and things like that.
Just to make sure, do you understand what do you mean by bind mounts? Yes. Okay, awesome.
Yeah, I have similar issues at my laptop, so I'm, it's good to know I'm not alone.
Yeah, it's pretty common.
Yeah, well, with that, thank you both for coming to talk. And
Thank you.
that concludes today's track.